At states of matter, then. You know there are 3 states, you may even know there are 4 states of matter. So let's look at the solid first. Things to note about solids. We have, we have a regular structure. There's the first thing. We have a regular arrangement of atoms or molecules. You would see this regular symmetrical arrangement right the way through the solid. You can imagine another layer like this one behind this, another behind that, another behind that, row upon row of atoms or molecules in nice neat lines, columns throughout the solid. Note they're touching. That's important because that makes solids incompressible. You cannot squeeze a solid. You can squeeze the empty space between atoms or molecules, but you can't squeeze solid particles or liquid particles or gas particles. You can't squeeze them. So because they're touching, this solid cannot be squeezed into a smaller volume. So that's one of your key properties of a solid. They are incompressible. This is also a key property, the way they're arranged. And you'll see how that changes as we go through liquids and gases. These atoms or molecules are bonded together. There are strong bonds. So it takes a lot to break these bonds. These atoms and molecules, they're vibrating in all directions. But that's all they can do. They can vibrate. Now, as you raise the temperature, as you supply thermal energy to your solid, those vibrations get faster because the temperature, which of course is going to rise when you supply thermal energy to your solid, is a measure of, the average kinetic energy of the molecules or the atoms. Now that's really important. Something for you to really get clear in your head. Temperature is a measure of kinetic energy of the molecules, but not just kinetic energy, but the average kinetic energy. That means some atoms or molecules, as we go through here, might have more kinetic energy than others. That's really important. So that's what temperature is. You're measuring the average kinetic energy of the molecules in your substance. So there's your solid. Regular arrangement, atoms and molecules are touching. That makes your solid incompressible. They are bonded together, so they don't slide past each other. So you can't pour a solid. You might say that you can pour sand. Well, yes, but what you have are little particles of sand, which are made up of lots and lots of atoms, or molecules in fact, all bonded together like this. But you've got little clumps of these broken up, and that's what your grains of sand are. You're not pouring individual atoms, or molecules rather. So you can't pour a solid. You absolutely can't pour a solid. My apologies for the poor writing. So that's solids. Regular, touching, incompressible, strong bonds, can't pour them. And this is a general statement which applies to all of our states of matter. But as you supply thermal energy, what you're doing is applying energy to the atoms or molecules. And so they are, in this case, in the solid, vibrating faster. Now it's important you talk about them vibrating. They don't move around, they vibrate. They don't go from here to here and leave the others behind. They don't move around, they vibrate. Okay, so there's your solid. Let's move on then and look at a liquid. So here we have a similar kind of arrangement, but there is a difference here. This is less regular. You're going to have some order, but over a much shorter range. The spacing between your atoms or molecules is about the same as the spacing in a solid. You might say, well, that's not really clear, we've got a space in here. Well, that's just an error in my making the diagram, really. But what I was trying to show here is that the order of these, it's not as regular, but they are as close together. Now that means liquids are also incompressible, because the atoms or molecules in your liquid are also touching, and so just like a solid, you can't squeeze your liquid. So you have less regular arrangement. The spacing is about the same as the spacing in a solid. That means liquids are incompressible just like solids. Now, these are free to move past each other. So you've got weak bonds here. In a solid, they were bonded together, strong bonds. Here you've got weak bonds between your atoms or molecules in a liquid, and so they can slide past each other. You can pour liquids. Now, in order to get from a solid to a liquid, if you imagine taking solid water, ice, to get it from ice into water, you have to supply it with some energy. What you're doing is you're breaking the bonds. We'll come back to talk about specific heat capacity, specific latent heat a little later, but you have supplied thermal energy. And there are two kinds of energy. Let me just talk about that while I'm here. So you have internal energy. This is the total KE and PE, kinetic energy and potential energy, possessed by the atoms or molecules. So one of the things we're saying with this, you'll have to be able to quote that. You might be asked, what is internal energy? You have to be able to say. But you can add thermal energy. You can take your solid, you can add your thermal energy, and that energy that you add might increase the kinetic energy, but it might increase the potential energy. Now, if it increases the potential energy and not the kinetic, then the temperature will not rise, because the temperature is a measure of the average kinetic energy. If you don't change that, you don't change the temperature. So it is possible to increase the potential energy, and potential energy is also kind of about order. So the more potential energy you have in your substance, the less order you have. Think about going from solid to liquid. You have less order. You have more potential energy. Even if the solid water and the liquid water are at the same temperature. So if you're talking about freezing point, you are melting your ice. They're at the same temperature, but there is more potential energy in the water because there is less order in the water. That's another way to look at it. So internal energy, really important concept, helps us to understand what's going on with changes of state, which we'll come back to. So I just wanted to mention that while I was at it. So we've talked about solids, we've talked about liquids. Then let's look at gases. So our gases then are really well spread out, these particles. So there is no order. This is random motion. We have large spaces between the atoms and molecules. We have, because they're so far apart, no forces. Now, in the real world, that's not quite true, but we don't deal with the real world until we're well into university. In terms of gases, we will always talk about gases being ideal, and one of the things about gases being ideal is there are no forces between the atoms or molecules in your gas. Now you can see we went from solid, very ordered, to liquid, less order, to gas, no order. How did we do that? We supplied thermal energy. So going solid to liquid to gas, you have order increases that way. And the internal energy increases that way. So I have to supply thermal energy to get from here to here. And at the point where I'm just changing from solid to liquid, I will be increasing the potential element of the internal energy, not changing the temperature, therefore not changing the kinetic energy. But as I heat my liquid up so that it moves towards the point where it will boil, I'm increasing the kinetic energy of my molecules. Then when I get to the gas, if you think about water, when water boils at standard atmospheric pressure, the temperature is 100 degrees centigrade. And it doesn't matter how long you boil that water for, it will still be at 100 degrees centigrade, but you will make steam. So again, just like at the solid liquid transition, phase change, change of state, the liquid gas change of state involves an increase in the potential element of the internal energy. And you can see we have moved the gas molecules further apart. So you can see how the potential energy is increased. There's a bigger space between them. You have physically moved them apart. That takes energy. So there you have solids, liquids and gases. And of course gases are compressible. You can squeeze a gas. We buy cylinders of oxygen for hospitals and cylinders of other gases for welding and that sort of thing. So you can squeeze a gas. You know that. You have these big spaces between them. You can push the gas molecules together, reduce the space between them. But once they become a liquid, you can't squeeze them anymore. They become incompressible in the liquid or the solid form. Now, another point occurs to me. When we talk about adding thermal energy and solids or liquids expanding, it's really, really important that you remember that with expansion, it is the space occupied by the vibrating or moving atom or molecule. And this, of course, is your solid. This is your liquid or your gas. Solids vibrate, solid molecules vibrate, liquid and gas molecules are moving around. It's the space occupied by these molecules that increases, leading to an increase in the volume of the solid or the volume of the liquid or the volume of the gas. It is not the atom or molecule expanding. Now, there are some things that you can say and just be wrong in an exam and just not get any marks for it. If you talk about atoms and molecules expanding, you might actually lose marks. So if you've gained a mark for something else you've said and then you talk about the atoms and molecules expanding, you could lose a mark for that. So there you have three states of matter. You have solids, liquids and gases. There is a fourth called plasmas. You don't need to know about that, but you might want to go and look that up for yourself if you're interested. Solids, liquids and gases. I have explained the arrangement of the atoms and molecules in them. I have explained the properties of them because of the arrangement and the bonding. I have talked about internal energy and what it is. I have explained how increasing the potential energy in your substance is decreasing the amount of order in your substance. I have told you that temperature is a measure of the average kinetic energy. And I've talked a little bit about changes of state. But we'll come back to that.